An introduction to combined heat and power technology, with a focus on stationary fuel cell application. What is combined heat and power? As we have learned, the second law of thermodynamics states that the total entropy of an isolated system can only increase over time. Basically, as energy is transformed or transferred, though the total quantity remains the same, more and more of it is wasted. An extremely simplified heat engine is shown. In a heat engine, this means there is an important measure, efficiency, which measures how much of the input energy ends up doing useful work. The equation for this is shown. As you can see, the efficiency goes up the greater the temperature difference between the hot and cold sink is. Unfortunately, engines can only be so efficient and much of the energy is wasted. But what if it wasn't? This is where the idea of cogeneration and combined heat and power technology comes in. Micro combined heat and power, or micro CHP, is the use of cogeneration on a small scale. There are 5 different electricity generating technologies: microturbines, internal combustion engines, closed-cycle steam engines, Stirling engines, and fuel cells. The first 4 can use fuel like propane, but we will focus on the fuel cell to maximize the sustainability of the system.
So what's actually happening inside of a fuel cell? Well, as the fuel cell inventor, William Robert Grove would say, you need natural gas or biogas, CH4, which has to be first turned into dehydrogen via SMR steam methane reforming technique. You need oxygen, O2, a catalyst such as platinum, and an electrolyte, which depending on the amount of electric power you are looking for, varies. Oh yeah!
The basic equation of the reaction taking place inside goes as follows. You have the hydrogen gas H2 and oxygen O2 as input, and you have water plus heat and electricity presented as energy as output. The cell layout is divided in 3 major parts: the anode, the proton exchange membrane filled with the electrolyte, and the cathode. In the anode, in contact with the catalyst, the dehydrogen separates into electrons and protons. They then reform the dehydrogen in the cathode to bond with the oxygen and create heat and water. Only protons freed by the catalyst can pass through the exchange membrane. As you can see, to reform the dehydrogen, the electrons have to travel through the electric line and produce electricity. And then, when they arrive in the cathode, they meet the catalyst. Depending on the electrolyte used, one fuel cell element provides around 1 volt, but stacked together, the total voltage is around 300 VC. Now, let's take the Canadian province of Saskatchewan, which has the biggest energy consumption per year, around 15,000 kilowatt-hour per capita. And let's compare it to a 5 kilowatt fuel cell. As you can see in that graphic, the fuel cell can accommodate almost 3 houses. One fuel cell is also capable of producing up to 16 million joules per hour at 60 degrees Celsius.
Micro CHP installations can therefore be used in a house or small business, and household units are sized between 0.5 kilowatts and 10 kilowatts. Fuel cells can raise the CHP unit's efficiency as high as 80 to 90%. They can operate without noise, produce no harmful exhaust, expel no breathable particulate matter or discernible smell, and they can blend in with other household appliances. In remote locations, micro CHP fuel cells can be an excellent source of on-demand backup power as they operate 24 hours a day. One of the downsides is that for now, systems have a high initial cost, ranging from around 30,000 to 70,000 Canadian dollars. However, over the past few years, the United States Energy Administration has reported the declining prices of fuel cell units due to factors such as technological advances, favorable incentives and policies, and the general interest in low emission profiles and distributed energy. With this comes the increase in use in multiple applications, and it is our hope that with this comes the further expansion into both the private and public market.